Okay, now we consider an example. So x squared y double prime minus 3xy prime plus 13 is 0. So this is a typical Euler equation. Alpha is minus 3 and the beta is 13. Okay. So for this equation, we take solution of the form y equal xr. Then direct computation tells us that applying the differential operator L to xr, we will get xr r squared minus 4r plus 13. Here, this polynomial of times 2 or order 2 is our capital Fr, capital Fr. And we need to find the root of capital F. Okay, so when let Fr equal to 0, we will see that r is 2 plus 3i or 2 minus 3i. So this is the case that we have complex roots. Lambda is 2 and mu is 3. Therefore, the solution is C1 x squared. X squared 2 is lambda equal to 2. And the cosine 3 log x. The 3 here, because mu, the imaginary part of lambda of our root r, is 3. So this is 3 log x. Similarly, the other solution is x squared sine 3 log x. Okay, so this is quite easy. So all our discussion is for x positive about Euler equation. For x negative, if we want to study the Euler equation for negative in the negative half axis, okay, how to do? So this has a problem because if r is a real number, xr does not always make sense. Okay, it is not always make sense. For example, if r is 1 over 2, then when x is negative, xr will not have real meaning. Of course, it can be considered as a complex number. And that will be treated in complex analysis, another course. So we don't want to get involved too much about this. Okay. So how to solve this equation? Instead of consider the solution of the form y equal xr, we can consider solution of the form y equal to minus xr. Because x is negative, then minus x is positive. So x power to the power r makes sense. Okay, so we consider solution of the form y equal minus xr. So we want to substituting this solution into the equation. So we need to compute the derivative of such y. So y prime using the composition of function. So y prime is r minus xr to the power r minus 1. Then the derivative of minus x, which is minus 1. So y prime is r minus xr minus 1. Okay, and this can be written as minus r absolute value of xr minus 1, because minus x is precisely the absolute value of x. Note that x is negative. Okay, so minus x is the absolute value. Now the second order the derivative. So we differentiating this. We differentiating y prime again. We will obtain y double prime. So the derivative of this y prime, the right hand side of the y prime, is r minus 1, then minus x r minus 2. But this minus x still need to taking derivative, which is x again. Therefore, this will give us another minus 1. Previously we already have a minus 1. So this is where this minus 1 square come from. Okay, so our y double prime is this, multiplied minus y1 square. But minus 1 square is just 1. And the minus x here is the absolute value of x. So this is precisely r minus 1, absolute value of x to the power r minus 2. Okay, this is the second derivative of y. So substituting all this into the equation, Ly is x squared y double prime, that is this, plus alpha x y prime, y prime is minus r, absolute value of x to the power r minus 1. Okay, then plus beta y is minus r to the power r. You will see that here x square is equal to absolute value of x square. Therefore, multiplying with the absolute value of x to the power r minus 2 give us the x absolute value of x to the power r. Okay, and the second term r, absolute value of x r minus 1, but we have a minus here. We have negative sign here. This negative sign can be grouped with x. This gives us absolute value of x. So in the second term, the power of the absolute value of x is also r. And the last term, minus x is precisely the absolute value of x. So all these three terms has an absolute value of x to the power r, and we take the absolute value to the power r outside. The other quantity combined together is exactly our previous quadratic polynomial capital Fr. So we see that Ly equal absolute value of x to the power r multiply capital Fr. So to choose an r so that such y is a solution, we only need to let capital Fr equal to 0. Therefore, this is precisely the same as the positive x case, except that we don't use x. Instead of x, we use the absolute value of x. Okay. So for example, we consider this equation. This equation we just studied. This is the equation we just considered here. But in this example, we consider the equation for positive x. Now our x is negative. The same equation. Okay. X is now negative. So the solution of this equation is precisely this. As before, is this for almost the same as the positive x case. But you only need to replace the x here by the absolute value of x. Therefore, the general solution is say 1 x squared cosine 3 long absolute value of x and the sine. Okay, this is the general solution. Almost the same as before, but only the x need to be replaced by the absolute value of x. Okay, so we don't need to consider this too much. And of course, our next topic is about the behavior of the solution as x goes to the singular point. Okay, this x square, our px is x square. So when x equal to 0, x squared is 0. Therefore, by our previous definition, such x is not an ordinary point, it is a singular point. So we are interested in the behavior of the solution as x goes to 0, goes to the singularity. Okay, so the behavior of the solution depends on the sign of the root of capital F, the real part of the root of capital F. And if the root is real, then the real part is precisely the root itself. But if the root is complex, so it has real part and non-zero imaginary part. So the behavior depends in great degree about which the real part of the root. So we consider several cases. If the real part is positive, because the solution is xr, in every case the solution contains x real part of r. Okay, so if the real part is positive, then as x goes to 0, the solution tends to 0. And if the real part is negative, then the solution becomes unbounded, because the solution has a factor x real part of r. Okay, so if real part of r is negative, and then x goes to 0. This is a negative power of x when x goes to 0. Therefore, it will be unbounded. But you cannot say that the solution goes to infinity. This is a different concept. Okay, you can only say that the solution become unbounded. Okay, and finally, if the solution has the loop R has imaginary part, that is, the imaginary part is not 0. Imaginary part not 0 means that in the solution you will have cosine and sine. So the solution will oscillate, and also the frequency will become larger and larger. That is, it oscillates more and more rapidly as x goes to 0. Why this is the case? Because in this case, the solution is cosine mu log x and sine mu log s. Okay, so when x goes to 0, the log x will go to negative infinity. Negative infinity, then you take the cosine, so the frequency will increase. Okay, so this is why we declare that the solutions oscillate more and more rapidly. Okay, so to get a feeling of the solution, all kind of solution, we will plot the solution. Okay, you might use the software I recommended to you previously, the GNOT plot, to plot typical solutions of our Euler equation. Okay, I will not repeat the plot here. You can do this yourself. Now, we consider another modular Euler equation. That is a solution equation of this form. It is not x squared but x minus x0 squared. So the singularity is x0 because px is x minus x0 squared. It is 0 when x equal x0. Okay. So for this equation, you can study such equation similarly. Simply consider solution of this form. Absolute value of x minus x0 okay. So I will not waste time in this topic.